Okay. So it looks like we're doing area and average value was the main topic today, area between two curves. So I've got some examples of both of those. So let's start with area, just regular area. And I was watching, I saw in class the inevitable question. I was waiting for it and I knew it was coming. Do you have to sketch the graphs? And the answer to that, I mean, if in some cases, if you can, depending on your ability to visualize like basic graphs, lines, maybe parabolas, you might be able to kind of set up the integral by visualizing it in your head, but you're essentially graphing it. You're just thinking about it in your head. But yes, by and large, you definitely want to sketch the region. But usually there's some exceptions. I know that one today was kind of a weird one. It was a sideways parabola. Most of the ones are lines, parabolas, the ones that show up on exams anyhow. So here we have a parabola and a line, and I'm seeing this parabola. One way to graph it is you could find the vertex, but if I set this equal to 0 and factor out an x, I can see that this graph's going to have x-intercepts at 0 and 2, right? Because if I set y equal to 0, that's what I'm finding. So 0, let's call this 2 right here. And because it's a parabola that opens up, I know the vertex is going to be below somewhere. So it's going to look, in fact, so this graph's going to look like that. This is y equals x squared. You usually don't have to find the actual vertex unless so that part's good. What we really need to know is where do these two graphs intersect and at what points? So y equals 3x, you should recognize as a line that's passing through the origin with a kind of a steep slope, but I know they're going to intersect, so it's not going to look super steep the way I've drawn my graph, but I want to show that it intersects right here, y equals 3x. And so we have some area in between these two graphs that we would like to find. Oh, yeah, here's the, I'll put it out to everybody. I'm not sure if anybody else came in. Here's the sign in. So the idea, as you saw, is we're kind of going back to earlier when we were finding areas underneath a graph. And remember, we were imagining filling up that region with a bunch of rectangles, right? You go back to, what is it, 5.1, I think, where we were doing Riemann sums. We were filling up a bunch of rectangles, and we realized that the integral, after we learned the fundamental theorem of calculus, that the integral was essentially adding up the areas of an infinite number of rectangles for us. That's what the fundamental theorem of calculus was doing. So now, when we were doing those, usually our graph was, part of the graph was above the axis. Maybe we did some where it was below. Here I have a region where part of it is above and part of it is below, right? So how do I deal with that? We're still going to fill it up with a bunch of rectangles. So you can imagine a bunch of thin rectangles here. Maybe I'll draw one here. I like to just draw a few representative rectangles throughout the region. And what we need to do, so the way to think of an integral is an adding machine, right? That's what we was doing before. It was adding up the areas of an infinite number of integrals. It will add together. That's why the integral sign looks like an S. It's summing up. It will add together whatever you ask it to, as long as you give it a correct formula for what you want to add. Since we want to add the areas of a bunch of rectangles, we need to provide a formula for the area of a rectangle, which is, of course, length times width, or maybe height times width. Height times width. And we want to add those all up. Let me start with the width. Trying to think if this has come up before. Possibly, but I'll say it again anyhow. The way to think of this, we now are going to have a new meaning to attach to this. And I think I've talked about this, but remember that the idea is these rectangles are infinitely thin. They're infinitely thin. So every single rectangle's width is an infinitely small increment of x. And that's exactly what we mean. So like if I put like underneath this width right here is dx. That's exactly what we mean by dx in this case. Yeah. So the width of this integral, every single rectangle's width is an infinitely small increment of x. So we're going to call that dx. So now we have kind of a dual interpretation here, right? Earlier, I told you that the dx kind of tells you what variable you should be integrating with respect to, and that is true. It has like a dual interpretation. Not only will this tell us when we do the integral what variable we should be working with, but it literally also represents the width of any one of these rectangles. Now, how about the height? You've talked about this in class, but maybe this will help if you were having trouble understanding that. Let's take this rectangle right here and let's pretend, so this one looks like it's right at about x equals 1 because it's between 0 and 2. The height of this rectangle is this length. This is the height. So how would I find that? Well, how high does this rectangle stretch? How would I figure that out? I would plug 1 into this function to 3x, and I can see that this rectangle right here, the height would be 3. And if I want to know how low this rectangle goes right here, then I would plug 1 into the parabola, right? Because it goes down to the parabola here. And 1 squared minus 2 times 1 gives me a y value of -1. Okay. So this particular rectangle goes as high as 3 and as low as -1. Who can tell me what the height is, or type it in the chat? What's this height? How many people agree it's 4, right? That's 4 units high is the height of that rectangle. Now, using the numbers 3 and -1, how do you get 4 from that? What do you do to those two numbers to get 4? How many people agree? So I can't write this in here. The height of this rectangle is 3 minus -1 gives me 4, huh? 3 minus -1. And so what that tells you is no matter what x value we're at, if I want to find the height, I'm always going to take whatever this top number is, which is going to be determined by this equation, and subtract what I get from this equation. So that's where that, you saw in class, when I want to find the height of one of these rectangles, we always want to do top minus bottom. And so for us, I did that for when x is 1. For any given x value, if I'm at some random x value, how high would it be? It would be 3x. How low would it stretch down? Well, it would be determined by the bottom function, which is x squared minus 2x. And then we'll multiply this by dx. And then the last thing is we need to tell the integral. We've given it a formula for the area of any one of those rectangles in terms of x. We need to tell the integral, where do we want to add these rectangles up from what x value to what x value? Well, our first rectangle is happening clearly right here at 0, right? You can imagine a little tiny one there. Our last one, sorry, I can't fit this all in. Zoom that out. Our last rectangle is happening right up here, which I don't know that x value yet, but I can certainly find it, right? Because that's the intersection of my two functions. I'll slide this up here for a second. To find this point, this is the intersection of this equation and this equation, which I can always find by setting them equal to each other. Subtract that over, that gives me -5x. factor out an x. This is in the way, but can you see I'm going to get either 0 or 5 as an answer there. The 0 I already knew, right? I know they intersect at 0, but now it tells me that this point, this x value is 5. This point is 5. I don't really need the y value, but if I wanted to, I could plug it into either one of these. It's going to give me 15. So our last rectangle we can now see is happening at x equals 5. Yes. Question is pretty much where it intersects is the first and last values we have to integrate. Yeah, if occasionally that's yes and no. I mean, the easiest questions, I think, or the most intuitive questions are where you're just finding the area between two curves where they intersect. But sometimes, you know, they'll give you questions. I think you've already seen one like with the, you did one with like a cosine graph or something, right? Like sometimes they might say, you know, you have a graph like this and another graph like this, but they want the area not necessarily where they intersect. They want like this area and then this area here. So, you know, it's not necessarily always where they intersect. We could maybe look at an example like that. Okay. We'll do this. So hopefully now you're getting pretty good at evaluating integrals. This isn't too hard to do this. So we'll just distribute this. So we have 3x minus x squared minus negative 2x is really going to be plus 2x. We could combine those two. So that's 5x minus x squared. And then your antiderivative, 5x squared over 2 minus x cubed over 3, evaluated from 5 to 0. Five cubed is 125. So if I plug in 5, I get that. And then if I plug in 0, fortunately, I get 0 minus 0, which is nice. So this is going to be 125 halves minus 125 thirds. Give that a common denominator. I multiply this one top and bottom by 3, this one top and bottom by 2. That's going to be 375 minus 250. I think that's 125 over 6. If I'm not mistaken. All right, let's try another one here. And don't be surprised, especially given the nature of your tests and quizzes, how you're, you know, really short amount of time. The hard part should be you should be, once you get to here, this should be like you've done enough of these, hopefully, that it's just cranking out the work, right, and finding the number. So a lot of times on tests and quizzes, just to make it a little bit quicker, so you don't have to do all the busy work, they might just have you set up the integral. So for example, if this one had just said set up the integral, I would have just stopped right here. I wouldn't have done any more work if it just said set it up for the area. Okay, so that allows a teacher to assess you, understand what's going on without, you know, keeping you busy for 10 minutes just adding and subtracting fractions and stuff, right? Yeah, the answer one more time. Yeah. No, I'm sorry, I go fast sometimes. So this one will just set up. We won't actually work out the integral. For the area in the first quadrant, that's why I only drew the positive x and y axis, bounded by y equals x squared, y equals 1 over x, y equals 9. In the first quadrant, y equals x squared would just be the right half of your parabola. So that would look like this. I'll leave it like that for now. Y equals x squared. Y equals 9 is just a horizontal line. And then that's a somewhat, hopefully you know the graph of y equals 1 over x. I'll remind you that the full graph looks like this. There's actually a horizontal and a vertical asymptote. The whole graph looks like this. That's one of your kind of the basic rational functions, like the easiest one that has vertical and horizontal asymptotes. That's what this one looks like. It's a good graph to know. So in the first quadrant, which is where we're focusing on, it's going to look something like this. That wasn't very good. And this is a horizontal asymptote. And admittedly, sometimes when they describe an area, it can be a little bit ambiguous. You're like, wait a second, I see, okay, to me, the top choices for what is the area bounded by these three graphs would be, because this is the graph now we see of y equals 1 over x right here. I see this region right here and this region right here as possibilities. The reason it's not this one right here is because that also would be bounded by the y-axis, which is x equals 0. And if they meant this, they would have put that in here. The only area bounded by just all three of those would have to be this region. Let me rewrite under here, y equals x squared. Now, now that we know the region, we can imagine filling this region up with a bunch of rectangles. And what I'm going to do is show you a couple of ways. You've kind of seen this. If I stick with my previous strategy, which was to fill this up with a bunch of rectangles, what I want to be thinking about when I set up this integral, as we saw, the height of any one of those rectangles, I'm going to write top function minus bottom function. And do you see the issue is that right here for both of these rectangles, the rectangles here on the top hit y equals 9. On the bottom, they run into y equals 1 over x. But over here, what changes? It's not the top function's the same, right? But now the bottom of these rectangles is determined by a different equation. And so there's no way I can do that. I can't, with a single integral, I can't like change my bottom function halfway through. So what if I was going to use vertical rectangles, what I would need to do is how about I call this region 1, this region 2, is I would need to use two integrals. Need two integrals because the bottom function changes. That was a changes, not charges. Okay, so one of the integrals, how about this? Let's just set it up. So here's what I mean. One of the integrals, my top function would be 9. My bottom function would be 1 over x. So it'd be 9 minus 1 over x, top minus bottom. And the second integral, top function is still 9, but my bottom function is x squared. Now, what do I need to be complete here? As I need to tell the integral where should I start adding these rectangles up and stop, And when should I then finish off by adding these rectangles? So I need to know some points here, right? Let's see. So let's start with this one right here. I didn't leave a whole lot of room. Where would 9 intersect 1 over x? I'm going to do the algebra over here. 9 equals 1 over x, because that would be this point, is going to happen when 9x equals 1. That gives me 1/9. So this point right here is 1/9, comma 9. This point here is the intersection of x squared and 9. I think that's pretty easy, right? X squared equals 9 when x is technically plus or minus 3, but we're obviously in the positive region. So this would be 3/9. And then this one right here is the intersection of 1 over x with x squared. If I multiply that over, that gives me x cubed equals 1, which is going to happen when x is 1. So this point is 1. If I plug 1 into either one of those, that gives me a y value of 1 as well. So then this first integral, where my rectangle's heights are 9 minus 1 over x, I would want to count those for between x equals 1/9. And my very last rectangle where that would be true for would be right at 1. And then from 1 to 3, this would be my formula for my rectangle's heights. And so this would be my answer for the area. Now let's suppose instead of a setup, we actually were required to find the actual area. Well, that's going to be annoying now because I have to do 2 integrals just to find this one area. And so what would be another option? Is it possible to find this area using a single integral? And the answer is yes. You talked about this earlier. So how would you describe this region using just one integral? How would you want your rectangles to be? Maybe that's a better question. Exactly. Yeah. If you line, I'm going to draw a separate picture here because I got too much going on here already. So I have y equals, we already know the region. If instead we fill up this region with horizontal rectangles, because the integral doesn't care. Like I said, an integral is just an adding machine. It will add together whatever you tell it to, as long as you give it the correct formula, it will work for you. So if we fill up this region with a bunch of horizontal rectangles, and what's really nice about this and how you can spot that this would be better is, do you see that that very top rectangle would line up perfectly with this horizontal line, huh? That would capture all of that area perfectly because it's horizontal. Now, if you're doing horizontal rectangles, then your formula changes a bit. Instead of top minus bottom, for the, I guess I'd call this the length of the rectangle now, we're going to always go right function minus left function. And then here's the other change. Remember how I was referring to the thickness of the rectangle? Now the thickness of any one of these little rectangles is a small increment of y. So we have to call this times dy. If you're doing horizontal rectangles, it's got to be a dy integral. Now back to that dual interpretation. Not only does dy represent the width of the rectangles, what that means is I need to express both of these functions then have to be in terms of y, don't they? If I'm going to do the integral, they better be in terms of y. So you have to do a little manipulation here. So remember, this equation was y equals x squared. And I know that every rectangle I draw in here is going to hit y equals x squared on the right side. But if I have to write that in terms of y, What is y equals x squared if I write it in terms of y? That just means solve for x. That would be x the same as x equals root y is my right function. My left function, y equals 1 over x. If I solve that for x, I just flip this side. If you flip that side, that's x. And if you flip y, that's 1 over y. So y equals 1 over x is the same thing as x equals 1 over y. And then also got to make sure your limits are in terms of y. I'm going to emphasize that by putting y here. And so this is a lot easier. Remember, I had to find these like points up here, but as long as I just know this point right here is 1, 1, where is my lowest rectangle that I would want to count? At what y value? It would be at 1. And where's my highest rectangle? At y equals 9. And you should probably try this on your own after class or something. This single integral should come out to be the same as both of those. If you combine those answers together, you should get the same answer because it's the same region. So what I would suggest is, as you're doing problems on this, sketch the region out, and before you just jump in, I would say that most of the ones you're going to see will probably work just fine with vertical rectangles. That's more common, vertical rectangles for most of the regions. But before you just jump into that, give a quick take and ask yourself, would it be better if I had a region if I filled it up with horizontal rectangles? Would it only require one integral if I'm noticing that when I try to do vertical rectangles, it's requiring 2, right? You might want to consider that. Or I've even seen plenty of test questions on this in my years, because I think it's a skill you need to know. And in fact, in 17C, we're going to revisit integrals. We're going to be doing double integrals. We're doing that right now in my 17C, and they're all happy about that. I'm joking. They're not happy about it. But anyhow, a skill you should be able to do is for any given area, be able to set up an integral using either technique. So I've even seen on midterms, here's a region, set up integral or integrals for the area. We're using vertical cross sections, and then for the same region, setting it up with horizontal. I think that's something you should know how to do. What am I doing on time? Okay, I got almost 20 minutes. Okay, so then that's kind of 6.1. There's certainly more types of problems. But then 6.2 is all about the idea of an average value of a function. So I wanted to give you an example of that. Find the average value of f of x equals 3x squared on the interval from 1 to 3. So I'm going to sketch that graph. This is a parabola. And we're really only interested in this between 1 and let's call this 3. So there's a formula for average value, as you saw. Here's the way I like to think of this. This was from a different calculus book I thought had a nice explanation of what the average value really means for something like this. And that's why I chose this particular function here. Okay, I'm going to just extend this. This isn't really part of the graph, but if I just extended this line right here, and maybe I did this. Okay. Try to imagine this as the side view. I tried to make this look like a cup. Here, maybe I'll put like a little handle or something like a mug. Okay. Okay, imagine this is a cup of water that somebody just bumped. Somebody just bumped, and so the water is swooshing up to the top. Can you picture that? Somebody just bumped this cup of water. So the water is all over the place, right? Its height is all over the place, right? The water, some water's up here at the top, some water's right down here. The height of the water is all over the map here, right? If we said what's the average value of this function, because the function itself is determining the height of the water, right? This 3x squared. If I said what's the average value, what that's kind of like asking is when this water comes to rest. Here, I'm just going to draw a separate picture. I will draw my same cup here. Eventually that water is going to come to rest and it's going to settle on a certain height, isn't it? When the water comes to rest. And that height, whatever this height is right here, this is what we mean by the average value. Average value is the height of the water when it comes to rest. What it's sort of a measure of, it's like an average of all of these heights, various heights of water here. And because it's not a linear thing, it's not a linear function, it's not just simply right in between. It won't necessarily be right in between this point and this point, which what would this be? If this was 3x squared, this would be 3. If x was 3, 3 squared is 9 times 3. This would be 27. It's not necessarily right halfway in between those two values. But here's what is true. And here's where the formula comes from. You know how a lot of times with integrals, we call this number A, we call this number B. So I'm going to label it here. B. Assuming none of the water escapes the cup, what should be true about the area? I know, because I'm just looking at a cross section of this cup of water. What should be true about these two areas? What seems intuitive if none of the water escaped the cup? How many people agree? It seems like they should be the same, right? Since it's the same amount of water. So the areas should be equally to each other. So how would I find this area? This would be the integral. I'm going to give you a general formula first, and then we'll work it out. It would be the integral from A to B of my function. And that area should be the same as this area. But this area is just a rectangle whose height is the average value, which is what I'm looking for, times what is this width in general? This width is B minus A. And since what I'm looking for is a formula for the average value, if I just divide both sides by B minus A, we get this familiar formula that you've probably looked at. The average formula, it's really over, but I like to write it as 1 over B minus A times the integral from A to B of f of x dx. This is the formula you've been working with. And so for us, for this function, we would have 1 over 3 minus 1 times the integral from 1 to 3 of my function, which was 3x squared. This is just 1/2. My antiderivative of 3x squared is 3x cubed over 3, so that's just x cubed. I end up with 1/2. 3 cubed is 27 minus 1 cubed is 1. 27 minus 1 is 26. Half of 26 is 13. So I guess in this context, this would be the average height of the water or the height of the water when it comes to rest. Average height of water, or the height when it comes to rest. Height at rest if we use that as our analogy. Let's see. So we've done just some kind of regular calculus here, right? Thinking about areas and stuff like that. But what we know is in this class, we like to see things applied. And that's certainly something to expect, right, for a quiz or a test and everything. So I was looking in the book and I found a couple of problems. I don't know if I'll have time to do them both, but I could at least do one that I could see as like good middle of the road application problems that I would certainly consider as a good test question to apply some of this stuff. I'll leave that last part there. This one's number 19 in 6.2. I'm paraphrasing because it's a little bit long. Basically what it's saying is a full respiratory cycle when you inhale and exhale, let's assume takes about 5 seconds. I just did it just a time. That seems about right if you're not like hyperventilating or meditating or something and trying to control your breath. That seems about right. And let's assume, well, I guess somebody knows this. Somebody figured out that the maximum rate of airflow into the lungs is about 0.5 liter per second of air. If you really, I don't know if that's breathing normally. That might be breathing normally, not like really trying to suck in air. Because even when you're breathing normally, as you get close to the exhale, you start to slow down your inhalation rate, right? So, this is probably right in the middle of your inhalation is when you're breathing in air the fastest. And so if that's true, then what the book says is that you could model this with this equation. F of t is your airflow rate of airflow in liters per second. And what I wanted to show you is some of this stuff, this equation right here, it's a sine graph. And they told us that a full respiratory cycle takes 5 seconds. So we have a sine graph that we want to end at 5, right? A sine graph. So let me put this in the middle. That goes up. And this would represent, here, I'll finish this first. So this would be positive airflow, right? That's when you're breathing in. So this part of the graph represents your inhalation. And this part of the graph is your exhalation, where you have negative airflow, right? This is negative down here. And they told us, so, and this is the equivalent to the amplitude of our graph, right? This is the 0.5 liter per second that they were telling us. 0.5 is the same as 1/2. So this is 1/2 right here. This sine graph goes down to negative 1/2. And some of you might remember that like the 2 pi over 5 is what you need, because a normal sine graph would finish at 2 pi, but if you wanted to finish at 5, you can figure out why that needs to be there, because what you would do is you would say your period, if you want it to be 5, is supposed to be equal to 2 pi over whatever goes in there. So if you solve for b, you end up getting 2 pi over 5. So that's why that's there. So just like in pre-calc, you learn this stuff, right? Now, what they're asking for, what is the average rate of airflow during the inhalation? So that would be right in here. We know at some point, I guess right here, right in the middle of your inhalation is where you're hitting your maximum airflow rate. But as you start your inhalation and as you finish it, it's not at its peak. So the average rate of airflow during the inhalation, which would be corresponding to time being between 0 and 2.5, right? 0 and 2.5. And so, you know, I already derived the formula. The nice thing about average value is you already have the formula. This is like our A and our B right here and here. So our formula for the average rate of airflow, average rate of airflow is going to be equal to 1 over B minus A. So 1 over 2.5 minus 0. Oh, I can't see that. Times the integral from 0 to 2.5 of 1/2 sine of 2 pi. I'm going to separate this out. 2 pi over 5 times t. Okay. Now to do this integral, the 1/2 can come out. In fact, what I'm going to do here, I'm going to make some room here, first of all. I like working with fractions better than decimals. I can do the calculations easier. So 2.5 is the same as 5/2. So this is really 1 over 5/2. I can pull this 1/2 out if I don't like it. We'll deal with that later. And I'm going to go ahead and write the 2.5 also as 5/2. Sine 2 pi over 5 t dt. Now to do this integral, there's two ways we can do this. When we were doing integration by parts, if you recall, I was telling you how you have to get kind of good at what I call a mini U substitution. I'm using a separate piece of paper here, so I'm just scribbling out here. Recall the idea of a mini U sub. And that was when I was using that was when I was telling you, is like when you integrate something like e to the 2x, where technically if you wanted to show it, you would let u equal 2x, go through the whole du thing. But the end result is the antiderivative of e to the x is e to the x. So this is end up being e to the 2x times 1/2 plus c. If you were integrating cosine of 3x dx, you could do another mini U substitution, let u be 3x and go through all that, or you could just argue once you see this, the antiderivative of your cosine function is sine, so it's going to be sine of 3x over 3 or times 1/3. Remember this idea when we were doing this with integration by parts? If you were doing sine of, how about this? Sine of 0.1 t dt. Why did I put x in dt? I don't know. Let's call this x then, and let's call this dt. Your antiderivative of your sine function is going to be negative cosine 0.1 t, and then for the same reason, I'm going to multiply by 1 over. I don't have a good place to put that, but I would be 1 over 0.1. Right, so if it's ever just a constant times your variable, just go ahead and find your antiderivative and do 1 over the constant. So you could do it this way. You could do it this way. Your antiderivative of sine of 2 pi over, this is just a constant, is going to be negative cosine of this times 1 over this, which would be like the reciprocal. If that is at all confusing, which I don't question that could be very confusing, go ahead and run through the U sub, right? I'll show it this way as well. So U would be 2 pi over 5t. Du would be 2 pi over 5 dt. Let's stick in red here. We'll deal with that in a second. So remember the way it works. Let's not even worry about the limits for right now. So if that's my u, this becomes sine of u, and all I have left over is a dt there, but I wanted to see a 2 pi over 5 dt in order to accommodate my du. So in this class, what we do is we do the wishing technique. So I would wish for a 2 pi over 5, compensate with the reciprocal, which is 5 over 2 pi outside. That's going to stay there. And then you're just left with sine of u, and this now becomes du. And your antiderivative of sine is negative cosine. So it's 5 over 2 pi times negative cosine of u. The other thing we've been doing in this class is if you want, you can switch the limits in terms of u, but sometimes I find that's more confusing for people. So I'm just going to switch back to t. So I'm going to put my u back in. I'll write this as negative 5 over 2 pi cosine of my u, which was 2 pi over 5t. But do you see how that's exactly the same as a mini u sub, right? You can, if you see it that way, by all means, go for it. Save yourself the grief of going through the u sub. I can't forget about this. So 1 over 5 halves is the same as 2/5 times 1/2. And then I have this, which I then need to evaluate from 5 halves to 0. Oh man, I'm going to need one more. I'm just going to use the bottom of this. You can start simplifying things along the way. This would cancel with this. The 5 would cancel with this. So it looks like I'm going to have negative 1 over 2 pi. If I plug in 5 halves, minus, okay, I can't forget about, okay, I took out the negative, never mind. I decided to take this negative out right here. So once I take that negative out, then it's just going to be minus the cosine of, if I plug in 0 there, that's just 0. Two pi over 5 times 5 halves is just going to end up being the cosine of pi. And the cosine of pi is negative 1 minus cosine of 0 is positive 1. Negative 1 minus 1 is negative 2. And negative 1 over 2 pi times negative 2 is 1 over pi. And the units here would be in, this was the airflow, this was the average airflow. So this would be in liters per second. And if you're curious, what's a very rough approximation for pi? Very, very rough approximation. It's like about 3, right? So this is about 1/3 of a liter per second is your average rate of airflow. Remember, the maximum rate of airflow when you're at the peak of your inhalation is 1/2 liter per second. So your average, and the average is kind of just like about what we were saying, is that if this was a cup of water in some weird way like this, it would be like the average height of the sine function in that interval. That's what that really stands for, that 1 over pi. All right, looks like, man, I only got through 4 pages here. I have another example about blood flow. We can maybe save that. We'll do that on Monday. Questions?
Thank you.
Oh, you're welcome. I will. Have a good weekend. Gonna get some rain, I hope.